So, who am I that's talking to you right now? Well, I am Luther. I am from Pensacola, Florida, so down in the South. It's been a long time since I lived in the South, though. I can still pull out a Southern accent if I need to get by every now and then, though generally doesn't happen too often. I went to school in Florida originally to a nice little liberal arts university on the beach. I chose it purely for its location. Fortunately, it happened to have a decent degree program as well, which helped me get into graduate school at Washington State University. I have now been at the University of Utah since 2014, so a little over 7 years. It's been a great time since I've been here, and I have a wonderful research team, and we have wonderful nuclear faculty that are here with me as well. So just to give you a little overview about what we have at nuclear at the University of Utah, I'm going to go through some of our capabilities, who our different faculty are, a brief overview of the faculty. I'm going to go over this pretty quickly because we do have 3 of our current graduate students on, and they represent 3 of the different research programs that we have in nuclear engineering. And so I'll let them kind of steal the show. And when I get to Dr. Shadeen's, he's on here as well, his research slides, I'll let him talk about those so that he can give you a little bit of overview about his research group. So you might be asking yourself, why would you want to do nuclear engineering and why would you want to do the University of Utah? Well, for starters, you already learned about how wonderful our location is. We're right here in the Rocky Mountains. We have wonderful outdoor activities surrounding us. We are a major metropolitan area and we have a nuclear reactor on campus. There's not really any other nuclear engineering program that can claim they have all of those wonderful things in the nearby vicinity. In addition to that, we have a really wonderful faculty and staff here at the University of Utah. We span a wide breadth of research that goes from nuclear forensics and nuclear safeguards, looking at how can we detect nuclear materials. Once we detect nuclear materials, how can we identify what they are or what they were intended to be used for? We do simulations of nuclear reactors or simulations of other nuclear components to identify how can we best streamline the experiments that we're hoping to do. And then we have a wide breadth of resources at the University of Utah. So we have the reactor facilities, as I said before, and then we have another 3,000 square feet of wet chemical laboratories for actually handling these radionuclides and doing the physical experiments that we want to do. Once we characterize those materials, we then have the ability to basically take them to any instrument on campus we want and look at them, which is really, really, really unique to the University of Utah. A lot of people won't let you put radioactive materials in million-dollar pieces of equipment. Fortunately here, they do. We have strict protocols for how we do it to ensure the safety of everyone in the process, but that means that the possibilities for your research are pretty much limitless. And if we can't do the research here, then that's where we lean into our collaborations with colleagues at national laboratories, and we send students there to do even more advanced experiments. So I'm going to go through a little bit of each one of these, and then we'll conclude, and I'll kick it off to the students to talk about their research. So why nuclear engineering at the end of the day? Well, nuclear has many positive contributions to society. One of them is the fact that it can be a source of green energy or carbon-free energy emissions. It does this by doing baseload power, so large amounts of electricity without having any CO2 emissions. Beyond doing just power production, though, nuclear has many positive applications from things such as nuclear medicine, which is what one of our faculty specializes in, Dr. Mastrin, to looking at nuclear material production and analysis for other applications. In addition, we might produce new nuclear materials that will support advanced reactor design, such as new fuels. Or we might do simulations of a new reactor core to design that next advanced reactor that we hope will be built in the next 10 to 15 years. In fact, one of our prior alumni from the University of Utah was an executive at TerraPower. TerraPower is one of the nuclear startup companies, which is kind of ironic to call it a startup company because their budgets are still on the order of several $100 million to $1 billion. But it was a startup company funded by Bill Gates out of Seattle for developing a molten salt-based reactor. And they're one of the few facilities that have gotten funding from the Department of Energy to build a test bed of that reactor. So pretty exciting things that have happened. As I said, initially, we do a lot of radiation detection and a lot of nuclear forensics. That's my specialty. Dr. Shadeen does a lot of research in that area. Dr. Cazalas does a lot of research in that area. And because the three of us do, we kind of force Dr. Bastrin to do research in that area, even though it's not quite her specialty as well. So with that said, all of our engineering faculty are looking to make advancements in the next generation of nuclear, whether that's developing technologies that help advanced power reactors or developing technologies that make nuclear safer so that people feel comfortable doing more nuclear power, or whether it's figuring out how do we recycle the waste coming out of nuclear power, or can we recover some of those isotopes to be used for medical applications. So who do we have at the University of Utah right now? We currently have 5 key players in the game. There are 4 faculty. Dr. Shadeen, he's the Energy Solutions Endowed Chair. We have Dr. Mastrin, who specializes in nuclear medicine. Dr. Kazelaz, who specializes in radiation detection. Myself as a radiochemist who does a lot of nuclear forensics. And then Dr. Vince Wang, who is one of our research scientists who does a lot on the simulations, helping literally everybody in terms of modeling different components of the experiments that they might have going on. So let's dive right into some of our facilities. Obviously, our big, very unique facility is our 100 kilowatt trigger reactor. It's fueled with approximately 20% enriched uranium zirconium hydride fuel. Within this reactor itself, we have several different irradiation ports, from our central irradiation port, which will have the highest flux, to a thermal irradiation port where a lot of the fast neutrons have been shielded, or a fast irradiation port where a lot of the thermal neutrons have been shielded. So this enables us to do a lot of different experiments in the reactor core, such as isotope production, or say we wanted to look at fission for a nuclear forensics purpose. Maybe we wanted to fission a uranium dioxide fuel pellet, look at the fission yield curve, or just look at how it changes overall. In addition to the reactor facility, we have many supporting large facilities as well, such as a dedicated radiation detection laboratory, multiple laboratories for radiochemistry, my favorite and the scariest laboratory on campus, the fluorine chemistry laboratory, where we get to make UF6 here on campus, but we don't do any enrichment or else the FBI would come and take us away from us. We have a nuclear medicine laboratory, nuclear materials laboratory, and we have extensive supercomputing resources on campus. In fact, the University of Utah has multiple supercomputers on campus, for which Dr. Shadeen's research group has even bought nodes into to have access to those supercomputers to enhance our computing capabilities. And in collaboration with the civil department, we have a wonderful, very large structure laboratory where if we wanted to test full size, say, structural materials that would go into a reactor core, we do have the ability to do that. So as a brief overview of some of the research that we do, Dr. Kazelaz, as I've said before, focuses a lot on radiation detection. So that could be detecting gamma rays, charged particles, or neutrons. He also looks at the radiation effects on electronics. So that's like electronic dosimetry. And that's very important for space applications. General dosimetry for health. And then all of these detection applications can also feed into nuclear security. And I know I went through that really fast, but Cody is on here with us as well, and he works for Dr. Kazelaz, and he'll talk about some of his research specifically. In terms of myself, we kind of have 3 main areas where we do a lot of analytical method development, which is what I would call signature development. So this is where we develop morphological signatures as well as stable isotope ratio signatures. We look a little bit at environmental fate and transport. This is looking at, say, how does uranium or plutonium behave in the subsurface and migrate from something like a long-term waste repository. And then both of these tie into new material synthesis, such as making new uranium-based materials that could be a fuel material that would have more structural integrity, that could be able to go to higher temperatures, or looking at how could we make these materials into stable forms that would not migrate in the subsurface. And Cody's going to talk to you quite a bit more about the research that we have as well. This is just some of the equipment that we have. I'm going to skip past this one just for the sake of time to make sure that the 3 guys up there have more time to talk themselves. Dr. Mastrin is also a radiochemist, and she is who focuses in nuclear medicine. And so whether that's developing radioisotopes that could be for targeted radiotherapy, such as targeted alpha therapy. She also looks at doing isotope production, and that production might be with a reactor, a cyclotron, or a linear accelerator. And in the process of doing experiments like this, she'll collaborate with someone like Dr. Shadeen to optimize what type of material should go in the reactor, where it should go in the reactor, and how long it should stay to maximize the isotope of interest that they're looking at. Then once all of those materials have been made, though, you have to purify them. And that's where they look at developing new resin materials or new extraction chromatography to be able to purify that isotope of interest. There's a few slides on her research as well. I'm going to skip past them because I know that George is on here and he's going to talk specifically about Dr. Mastron's research too. So up next is Dr. Shadeen. So Dr. Shadeen, if you want to unmute yourself, I think there's a couple slides about you if you want to talk about it.
Good morning. I will be very quick because I have a reactor meeting coming up, so I won't spend a lot of time. We are doing, as Dr. McDonald said, we're doing a lot of optimization with the reactor. The photos here show one of our grad students, Tanner, who's working on an optimization project for optimizing xenon 135 production and minimizing xenon 133 production, because you get an end-to-end in capture from xenon 134. And we're trying to minimize that end-to-end because xenon 135 has a very much shorter half-life than 133, and we're trying to optimize the 135. So that's kind of really interesting. We're doing that for INL. And all of this is part of, we do a lot of computation and a little bit of experimental, and that complements everyone real well because we have several folks like Dr. McDonald and others who do a lot of experimentation, and we try to support that work as much as possible. So it's a very symbiotic relationship among all the faculty to try to help them optimize whatever they're doing. And we use a lot of high performance computing. We have some really world-class high performance computing at University of Utah. So next slide. So run the crit cell group, and our view is if you can calculate it, we can perform the research to optimize it, ultimately optimize it. We do every kind of calculation, including radiation transport, heat transfer, you name it, anything we've got to do to get the solution and model the system. So we're in the middle right now of doing some very high fidelity 3D burn-up assessments with a new algorithm we recently developed. So we're working on that. We're working on, I just sent a proposal into Los Alamos where we're looking at fission products from underground nuclear explosions. So we're going to try to do that with them. So there's lots of things you can calculate and do testing and evaluation. And we try to work again with all of the faculty to create new devices, new methods, new anything you can do to design a system and do system analysis. Next slide. So we've recently completed a very thorough modeling of our reactor, so we know exactly what the flux is everywhere. And the bottom slide is that 135 to 133 xenon ratio that we were talking about. But we have a very detailed 3D model of the reactor, and we're now reconstructing the burn-up history of the reactor. So we're working on that. So lots of cool things you can do with the reactor and isotope generation and other things. So next slide. So I'll turn it back over to you, Luther.
Awesome. Thank you, Dr. Shadeen, for joining on and giving us that overview. So
thank you so much.
Yeah, no problem. So just to summarize up what we have in nuclear here at the University of Utah, we have a lot of research that goes into radiation detection and materials testing. We do a lot of forensic analysis. So this might be helping identify unknown nuclear materials or safeguarding materials that have been declared and that we know are in part of the nuclear fuel cycle. We do a lot of research in nuclear medicine, looking at how can we develop new isotopes for cancer treatment or for imaging in medical applications. We look at doing nuclear global detection to ensure the safety of all nuclear reactors globally. And then we also do a little bit of reactor engineering and design, looking at how can we develop those new generation 4 reactors that are going to be safer, have higher efficiency, and basically can't undergo some of the extreme accidents that have been observed in the past. We also have extensive modeling capabilities which support all of the wonderful experiments that can be done. And really, that's one of the beautiful things that we have here with our group of faculty is that we have really nice experimentalists who can say, okay, well, let's go and do an experiment of this. And then we have modelers that can help us interpret what are the results from that experiment, or that can help us decide what is the next experiment that we should do. I know that all of you are on here for our graduate programs, and so specifically the PhD program or the master's program. Hopefully the PhD, if you're considering nuclear, I encourage you to go all the way. You'll have a lot more opportunities with a PhD than you would with a master's. All right, with that, I'm going to kick it off to George now. And George, I will click through your slides for you, just like I did for Dr. Shadeen.
Awesome, thank you. So my name is George. I'm from St. Louis, Missouri, and I am in my second year of the PhD program here at the University of Utah. It kind of feels like a mix between my first year and fifth year with the coronavirus pandemic and everything being shut down. So time's been feeling a little weird, but I'm about to be finished with my coursework this semester and planning on taking the qualifying exam. And I'm going to go over just a little bit of my research. I work with theranostic nanoparticles, meaning that I make nanoparticles to diagnose and treat different types of cancer. And I'm also going to take you through a little bit of the isotope production that Luther mentioned, and then I have some photos of hiking and skiing. Go to the next slide. And so these are some of the nanoparticles that we make. On the right, you see some silicon nanoparticles, and in the bottom left, you see some iron oxide nanoparticles. And these normally have a diameter of about 10 to 100 nanometers, depending on the synthesis conditions. And to put that in perspective, your fingernails grow at about a nanometer per second. So in about the time the slide's been up, your fingernails have grown longer than the diameter of some of these nanoparticles. So they're very, very small. And if you can go to the next slide, after we make these nanoparticles, we need to incorporate our radiometals of interest. And in our lab, we specifically work with actinium-225, which is an alpha emitter that we use for targeted alpha therapy. And we're really excited about this because alpha particles have a very short half-length on the order of less than 10 cells. So they can be targeted very well to tumors, especially small tumors, and deliver lethal radiation doses that cause double-strand DNA breaks inside the tumor while minimizing the dose to surrounding healthy tissue. And then in the same nanoparticles, we also incorporate zirconium-89, which is a positron emitter, so that we can image these nanoparticles in vivo to predict and monitor treatment response and also detect cancer recurrence. And with that, we've gotten pretty good results showing greater than 90% labeling of both of them. The silicon nanoparticles are being a little tougher, but that's kind of where I'm at in my research right now. And then in the future, once I have these nanoparticles with the radiometals inside, I'm going to attach different peptides to target tumors. And specifically right now, we're working with octreotate, which targets neuroendocrine tumors. Next slide. And then another project I'm working on is the photonuclear production of actinium-225 in collaboration with Idaho National Lab. And they use a Bremsstrahlung interaction to create high energy photons to bombard radium-226 for a gamma-N reaction to produce radium-225. And then that radium-225 is then beta decays to actinium-225, which is our alpha emitter of interest. And so that's all done at Idaho National Lab. And then they ship us these samples, and we work on the chemical separation for these. And we use a branched EGA resin to do this. And the graph in the bottom right is showing that just some initial studies where we've been able to elute radium with 6 molar nitric, and then we've been able to recover the actinium afterwards with 10 molar nitric. And we're seeing a pretty good recovery, which we're pretty excited about so far. You can go to the next slide. And these are just some pictures about life in Utah. The top right is from a trip to outside of Denver, which is about 7 hours away. And then the other 3 are either within an hour or 2 to 3 hours in the Wasatch or the Uinta Mountains. Basically, when it's nice outside, if I'm not in lab, I try to get outside hiking. And then on the next slide, when it's cold outside, these are a bunch of Utah ski resorts. I never skied before I got here, but Dr. Kazalez is actually a ski instructor, and he taught me on my visit, and I've just grown to love it, and it's been a great time. And I think that's all I have.
Awesome. Thank you, George. All right, Cody, it's off to you.
Hey everyone, I'm Cody. I'm from Knoxville, Tennessee. I did my undergrad at the University of Tennessee in nuclear engineering. And during that time, I, you know, began working in research with nuclear forensics. And I just loved it so much that I had to continue it during my PhD program here at the University of Utah. I work for Dr. McDonald, and I have done so since the fall of 2018. And so I'm gonna, oh, let's go to the next slide.
Yep. So no pressure on this presentation if you mess up.
Yeah. So a lot of the research we do in Dr. McDonald's group looks at the surface morphology of uranium as well as the stable isotopes, but that's not really my field, so I'm going to focus on the morphology. And so what makes morphology a interesting signature is that it will tell you things that other analytical techniques will not. So we've focused a lot on these materials: ammonium diurenate, ammonium uranyl carbonate, magnesium diurenate, sodium diurenate, and uranyl peroxide. And so when you produce these materials and calcine them to intermediate products that are important to the nuclear fuel cycle, such as UO3, U3O8, UO2, an analytical technique like powder X-ray diffraction will mostly show the same exact spectra for UO3 produced by any of these 5 precipitation routes. But as we can see from this image, there is a very large difference in the surface morphology when viewed by scanning electron microscopy. And so this is sort of what we're getting at with using this as a signature, because there's not many other good ways that can quite as definitively give you information about what precipitation route a material might have been processed from, and that can in turn begin to tell nuclear forensics investigators what sort of facilities the material was produced at, an unknown material. So next slide. In addition to these precipitation routes, there are a lot of other factors that affect morphology that the research group has been investigating. Among these are precipitation conditions. So, things like the amount of uranium in your solution, the strength of the nitric acid in your solution, as well as stir rate will all affect how these particles look when precipitated and calcined. Calcination temperature. So early research also looked at, if something was calcined at 700 degrees Celsius to U3O8, can we tell a difference between a material that was, say, calcined at 800 degrees Celsius? And then additionally, there's been a lot of research into how different elemental impurities, chemical impurities in the materials at the time of precipitation can affect the morphology. So these top two scanning electron micrographs, on the left, we have a control material. So this precipitate had no elemental impurities. It was precipitated as uranyl peroxide. The precipitate was not washed, so it had a lot of residual nitrates when it was calcined. And then on the right, we have a uranyl peroxide that contained some zirconium at the time of precipitation. And we can see that these images are on the same scale, taken at 50,000 times magnification. There's a huge difference in the way these materials look, despite coming from the same precipitation route. And this work, all the work on this slide was actually carried out by my colleague Alexa Hansen. And so on the bottom, we have an unaged uranyl peroxide that's been converted to U3O8. And then after aging for 60 days in like cycling, so it would go from a high temperature, high humidity to a low temperature, low humidity. We, over the course of 60 days of cycling, 12 hours at the high conditions, 12 hours at the low conditions, we see a huge change in the morphology, which can provide a signature about the history of this material. Next slide, please. And now getting into some of my work, my first project here, I was looking at the morphology of uranium ore concentrates, or UOCs, that were produced by different solvent extraction routes. And what made this project unique is that I was starting from an actual uranium ore. I leached out the uranium by sulfuric acid leaching, and then purified by 2 different solvent extraction routes that are representative of what you'd see in an industrial milling process. And then I precipitated the materials as ammonium diurenate and calcined them under the same conditions. And what this gave us was realistic impurity patterns that fit the kind of impurities that we would see in real world uranium ore concentrates. And then we also were able to identify unique surface morphology. Next slide, please. So here we can see the difference in the DAPX solvent extraction route on the top and the AMX solvent extraction on the bottom. Qualitatively, the big difference here would be something we'd look at is like the density of the agglomeration of the microparticles. We saw like tighter agglomerations with the AMX route, as well as a higher purity product as identified by mass spectrometry. And then another way we look at particle morphology is by measuring the actual size of these microparticles using a segmentation software, and then using statistical tests to determine whether or not these would be statistically different and in what way. Some work I'm really excited to be kicking off in the next couple weeks is a project looking at uranyl fluoride or UO2F2 morphology. And this is a very important material for later on in the front end of the fuel cycle. Most of our work is focused on what would be produced as uranium ore concentrates, whereas these are the intermediate steps leading up to UO2 fuel production, the precursor powders for sintering pellets, as well as possibly going to UF4, which is important for producing uranium metals, which is uranium metal is a very important material for bomb production. We won't be going into UF4, but we will be producing UO2 by a couple different routes. And then rather than looking at other elemental impurities, we're going to be focusing a lot on fluorine and seeing if there's any correlation between morphology and fluorine concentrations. Additionally, machine learning, particularly with convolutional neural networks using our scanning electron microscopy images, can be a very important tool for identifying the processes that produce these uranium materials. But we still need a little bit more work before it's an entirely usable tool. And so one of the things we need in particular is uncertainty estimates for our predictions. This is something that's right on the the leading edge of machine learning research. And so this is something that I've been working to apply to our uranium morphology images. And then also explainability. Sure, we can get good results out of convolutional neural networks, but before this is a tool that can be used as evidence in a nuclear forensics investigation, there needs to be a little bit of work to explain why we're getting these results. And then additionally, we need the ability to generalize to out of distribution data. And so earlier I went through all the factors that affect uranium morphology. And so what happens if we get a uranium material that is unlike anything we've ever seen before? How well are we able to predict that? And what kind of changes in the material can we correctly identify right now? And what do we need to produce more data for in the future? And I think I've gone over most of this. So yeah.
Awesome. Thank you, Cody. Or thank you. Yeah, I have two Codys back to back. How did I not notice that until now? Wow, how confusing. All right, Cody number 2, you're up now.
Yeah, so I'm the other Cody in the nuclear program. I came here in fall 2019, and I've been working under Dr. Kazales since then. I'm originally from Lamont, Iowa, which is a tiny town in Iowa, about 150 people. I got my undergrad in physics and math from Wartburg College in Iowa. Next slide, please. So one of the things that I focus on is producing a neutron irradiation facility. I am not a chemist, so I'm getting away from the chemistry side of things. So we have a 2 Curie plutonium beryllium source on campus. As of right now, it hasn't been used since around 1970. We don't have very much documentation on the source. We don't know its current activity, and we overall just don't have a lot of information with it. and that makes it extremely challenging to actually create this facility to ensure we've met certain things like dose limits to the public, occupational workers, and things like that. So one of the things I've been working on is a GEONT4 model and simulation of it. So GEONT4 is a Monte Carlo simulation tool for radiation transport. GEONT4 stands for Geometry and Tracking. It's developed by CERN. Down on the bottom right there, you'll see there's a emission spectrum for the source that we have estimated, as well as some scored spectra for neutrons and gamma rays from the source as well. Next slide. So one of the things I was saying, the current activity in emission spectra can only be estimated right now because we don't have access to the source at the current time. Once we are able to actually remove this source from where it's located now, we'll be able to get better estimates and measurements of it at that time. One of the things we need to focus on, like I said, is adhering to public dose limits that are set through NRC and 10 CFR 20, things like that. And right now I'm actually in the construction phase of this facility. And that is hopefully going to be done in the next month or two, is my hope. Next slide. So this is some of the data that I've been collecting for that. Up at the top is the emission spectra, like I showed before. Down on the bottom left is showing the dose rates that I calculated with GEONT4 from this source in various locations of its operational stages. So you can see between storage, operation, and in air, there's a dramatic difference between the dose rate that we expect at various locations throughout wherever that source is going to be located in the facility. And on the right, the biggest part of having this irradiation facility is to actually use the particles that are coming out of it. So we designed a beam port into this facility, and we're actually aiming to characterize this experimentally. And this is an image of the neutron distribution coming out of that beam port that I simulated in GEONT4. And that's it for that. The other thing I've been working on are testing helium-3 and boron trifluoride proportional tubes. So helium-3 is currently the most popular proportional gas that is used for neutron detection. Naturally, because it's the most popular, there's a global shortage of it. So we're running out of helium-3 that we can actually use for these. So boron trifluoride is being tested as, well, it's already an extremely popular proportional gas, and it's being studied now as a direct replacement for helium-3 tubes that are already in use. So one of the things that I'm aiming to do with this is to validate some prior simulation work that has gone into some of these tubes to actually experimentally test whether or not those simulations are accurate. So this is just an experimental setup that I have. That's a crypt that I built by myself because I was bored one day. Next slide. And these are some spectra that I took from those helium-3 and BF3 tubes. So the helium-3 up at the top left, what you see there is basically the epithermal peak from a neutron capture. And down on the bottom right is the boron trifluoride spectra, where again, you'll see the large epithermal peak on the right there. And I think that's about everything I had.
All right, thank you so much, Cody. So that is pretty much the end of our presentation. There are a few additional slides that I have on here which just show a little bit of the difference between a master's degree and a doctoral degree. If you're looking at doing a non-thesis master's, generally that's going to be completed in around 3 to 5 semesters. So on average, our students finish within 2 years. If you're looking at doing a doctoral degree, generally average is around 4 years to 4.5 years. I will say I've had one student who finished in 3.5 years, going from a bachelor's to a master's. So it can be done faster than that. It is not necessarily the average, though. I would expect to be here around 4 years if you were going to go for a PhD. Then beyond that, there's just a lot of pictures of our wonderful campus. Some of you may know we hosted the Winter Olympics in 2002. Salt Lake City is one of the finalists for the bid of the 2028 or the 2032 Winter Olympics as well. The opening ceremony was held on the campus in the football stadium at the University of Utah. So it is a pretty stunning campus. It's a huge campus. There is a lot to do here if you wanted to come here, besides just your schoolwork, though the key is that you hopefully like your schoolwork. So I guess to conclude this little nuclear session before I open it up for questions and discussion, there's two pieces of advice I always give every student looking at doing graduate school. So the first one is that you've got to like where you are and what you are doing. If you're not passionate about your research or you hate the place that you're living, it's going to make grad school pretty miserable. So make sure that whenever you do decide on your final place, that the project is something that really piques your interest and it's something that you want to dive into and you want to make new discoveries for because you want to help the world in that type of advancement. In addition, make sure it's somewhere that you want to live for 4 years of your life. Maybe that's that you want to get to a new part of the country and experience that part of the country. Maybe it's that you're from Salt Lake City and you go, you know what, I know Salt Lake is just the place for me. I'm going to stay here. That is all perfect. Throughout my career, I have moved all over the place, mostly because I wanted to live in different areas of the world. I mean, I went from Florida to Washington to France, back to Washington, down to Utah, to California for a little bit, back to Utah. So I think that that's the beauty of getting an advanced degree, is it just opens up so many different opportunities that if you want to explore the world, you have the opportunity to do that. If you look at Salt Lake City and go, this is the perfect place for me, which it's a wonderful place. It's the longest I've lived in a place since I grew up in Florida. I think it's worth it as well. So that's why I've been here for over 7 years, and hopefully you enjoy these different opportunities and these experiences. So I'm going to stop sharing my screen at this time. I believe that we have about 10 minutes where we can just have discussion. It looks like I have Courtney and Wendy in the room. I'm pretty confident they wanted the discussion to occur in the chat panel. I will say, I believe I know everyone that's in here. Would I be allowed to open up the microphones, or is that going to get me fired from the university if I do that?
I think you can open it up.
Okay. Let's see if I can make that happen then. There you go. Okay, Matthew, I saw I got your unmute done. Logan, I got yours on. Sam, I got yours on as well. Okay. Do you guys have any questions, discussions? It can be for me, it can be for the graduate students, it can be for anyone.
I have a question, I guess. How would you decide whether a PhD or a master's degree is right for yourself?
Yeah, absolutely. So they are two dramatically different commitment levels. So a master's degree you will finish in a 2-year time period. And the master's degree is a coursework only degree. So you won't be doing any research for it. You'll just be taking 3 to 4 classes a semester until you reach the minimum requirements for that master's degree. With a master's degree, generally you would go and work at something like a power facility or a regulatory based facility, or you might be like a radiation control specialist at a national laboratory, where you're just making sure that experiments are done safely, you're operating a reactor, or you're just doing routine business that is expected of the nuclear industry. But with the master's level, you're generally not innovating and pushing it to the next level. That's kind of the difference, is you have that base knowledge that you can operate everything safely, you know what it is, you can perform the experiment that someone else tells you to do, but you're not really developing what that next experiment would be. So that's how I would describe them. And for a lot of people, they enjoy that aspect of it. And we need people that do that. And then there's other people that go, I want to be the one designing the experiment though, not just doing the experiment. And if that's the kind of person that you are, then I would say go all the way for a PhD. Great question.
I have a question.
Sure, go for it, Sam.
Yes, with the COVID situation, everybody's teaching online. So I don't see that going away anytime soon. So is it master's going to transition to online, to fully online?
Yeah, so that's a great question. Right now, the university's plan is to actually be in person in the fall. So there is a lot of advancements that are being made with the vaccine and the vaccine distribution. And obviously all of those changes could, be different depending on the month that we look at and we see how the vaccine distribution is going. But as of the current path, the university hopes to have the majority of its classes in person in the fall. Even right now, at the graduate level, because the classes are smaller, some of the classes are indeed in person. And that's because we can put like these small 10 people classes into a classroom that fit 50 people so that you can easily maintain your social distancing in a classroom of that scale. So if you were to come in the fall, there will certainly be some classes that will be in person. I have no doubt about that. If there are some classes that are online, we've gotten pretty good at our online teaching as well. And so we teach either live via Zoom, which means it's just like this. So I see you on the camera, I share my presentation slides. In fact, George and Cody are in a class that I'm teaching live by Zoom right now. I think it's going well. Hopefully they have the same perspective. We also have asynchronous online learning, which is a fully online course. And for generally, those are only at the undergraduate level though. And that's where everything would be like pre-recorded lectures or pre-recorded lessons that you would do on your own. But in all honesty, I would expect the majority of our classes to be in person in the fall based on how things are currently going, knowing that it can change because coronavirus has changed the world and how we operate for sure.
I was just to add on to that from a student perspective, all of the classes that are in person, they're requiring weekly COVID tests for all of those students. And that's administered at couple different places on campus, and it's relatively quick. I think you get your results, they say within 2 days, but normally it's within 24 hours. And even if you are a student that doesn't have in-person classes, they're still available to you on a weekly basis. So right now, all of my classes are online, but I'm still going into the lab because I can't really do my work at home. So I've been getting weekly tests, and it's relatively painless and pretty easy.
I'll say there's also classes in the nuclear department that just are difficult to do online to begin with. So I know Dr. Shadeen has taught his reactor physics class in person the entire time, just because it's just a class that kind of requires being in person. And on top of that, things like nuclear instrumentation, where you have to be physically in the lab, you can't really do that online. So even if things do go online, there will still be a portion that will be in person, I believe.
I got a question about different topic, but I was just curious for, I guess this could apply to either, but mostly just the PhD program. I'm curious what changes the amount of time you're there. I'm just kind of confused as to how someone could graduate in 3.5 years as opposed to like potentially 5 years, when it seems like the requirements are sort of set in stone in terms of classwork and research.
Totally. I can answer that. Cody, it looks like you unmuted. Do you want to take a stab?
Yeah, I'll take a stab. There's just a lot of uncertainty in research sometimes because as a PhD student, you'll be working under a professor who has research interest, but you'll also have some leeway to figure out what you want to do within that. And you'll be designing your own experiments a lot of times. And so not everything goes according to plan. There's times that you'll have to, just remake your replicates for your experiments. There's times where you'll have to scrap parts of an experiment entirely and just start from scratch. The coursework is pretty set. You typically finish that within the first 2 years, at least all your core classes, and then you'll take your qualifying exam, which basically is it's a big written test that tests you over every core class that you do. But then after that, like I finished up classes last spring, and I've just been working on research since then. And I'm targeting about 3.5 years as well. But not everyone's research goes, and it never goes entirely according to plan, but some people's research goes less according to plan than others.
Yeah. And so there's a couple things that I'll add into that too. It's also a very self-driven thing doing research. Like Cody said, you will all finish your coursework around the exact same time. And while you're doing that coursework, you'll also be doing research. Though generally the research is a little bit less because, well, you're also taking 2 to 3 courses a semester. So you just don't have as much time. But that's where there is a minimum commitment for research. And then there's how much research do you want to do? You know, maybe the minimum commitment for the semester that you're in is 10 hours of research a week. And if you do that minimum, then you're probably going to graduate more towards the average of that 4.5 year time frame. If you're someone though who's really passionate about your research and you go, hey, I don't mind staying an extra hour or an extra couple of hours because I really want to see the results that this experiment's going to give me, then those are the kinds of students that generally finish much ahead of schedule as well. So it kind of, again, that goes back to like my two things for picking grad school, really liking the project that you're going to do. Because if you really like it, it makes it so much easier to finish all of that work. Whereas if you don't like it, you're generally doing the minimum just to get by, and that's when it can drag out your degree. And then I can also speak to Cody's. Sometimes experiments just don't work. For me personally, I did 3.5 years of research without ever getting any bit of data that could go into a publication. It was literally 3.5 years of trial and error of troubleshooting. And then at that 3.5 year mark, I literally got all the data for my entire dissertation in like a 2-month period, because I had finally worked out all the kinks, you know, and that is not the ideal situation at all. I never want a student to go through that. I actually have a student who is doing that right now, working on my fluorine line, where he literally spent 4 years troubleshooting this fluorine line, getting it to work. And then once it started working, it's been nonstop getting data that's going to go into publications. So his dissertation's going incredibly fast now, but that's just an example of, that was just an incredibly hard research project that it wasn't for lack of the student working either. It was purely just the experiments weren't working. And sometimes that happens.
So I have another question.
Sure.
So I'm interested in radiation health, and I see that the coursework correspond to radiation health.
Yeah. So if are you looking at doing the master's or the PhD, Sam?
Right now, I like to do PhD, but I'm kind of looking at the master's.
Okay, totally. I can talk to you about both of them and what radiation health might look like for you if you wanted to do them. Within nuclear engineering, we have 4 cores in this program. So we have radiation interactions, radiation detection, reactor physics, and health physics. So health physics would obviously be a class that would be very much of interest to you because of the radiation health impacts. But to understand health physics, you have to understand radiation interactions, because it's interactions that are driving the chemistry, or not necessarily the chemistry, but the damage that's being done in the body. So you have to know, how is this alpha particle going to deposit its energy so that you can do a dose calculation in health physics. Likewise, understanding how to detect radiation plays a critical role, because if you can't detect how much radiation is there, then you can't estimate what is the dose that's going to be given to a person based on that type of environment. So while the courses may not sound specifically related to health, all of them contribute to that health aspect. And then health physics would be a course that you would take that would be the direct application of basically all of the fundamentals of nuclear. So those are the 4 cores in nuclear. In addition to those 4 cores, you would take 2 additional nuclear engineering courses, and those could be really anything that we offer. But then to get your degree, you would have to have 4 additional courses on top of that. So 30 credits in total, roughly 10 classes. Those 4 classes can come from any other major at the University of Utah. And this is where we are very lucky to have one of the largest medical schools in the Southwest, and a medical school that's continuously ranked in the top 20 in the nation. And they have a huge radiology department for which students are welcome to go and take classes in that as well, that could contribute towards your graduate degree. So if you were particularly interested in the health aspect, then I would encourage you to work with Dr. Mastrin, because she is our nuclear medicine one, and she's the one who would have those connections to the medical school. And she could help steer you towards other classes that would be beneficial specifically to your research of interest. And George might be able to talk about that a bit, because I know he's had to take some different courses than our traditional nuclear engineering as well.
Do the students that are interested in nuclear health, nuclear radiation health, do they do research in the hospital?
You could do research with people that you collaborate with in the hospital. though generally like studies that are going into like patient studies are very advanced research studies. And most of what we would do in nuclear engineering would be the fundamental. So developing the isotope and the target molecule to be able to use that. And then it would go into like clinical trials of doing the studies on mice or something of that nature before they went to human trials. Human trials are really, really, really far along. So we could potentially do that, but generally that would be done by a medical doctor, not by people in our department. George, I don't know if you want to add on anything to that.
Yeah, my research it's different than what you're interested in, so I can't really speak directly to it. But with working with different departments on campus, we collaborate with different people in chemistry and pharmaceutical sciences, and we are hoping to do a couple in vivo mouse models before I graduate. But it will all be preclinical research, and like Luther said, like actual human trials is kind of out of the scope of any of our interests. And it looks like the breakout rooms are about to end.
Okay. Any last questions before they send us back to the main group?
How did you guys find what your research topic was? Like, what is interesting to you guys? I know that you probably can't answer that in the time, but
Or did you just grab the research topic that you were presented with?
For me, I got really lucky and I applied to like 30 internships and got rejected from all of them except a radiochemistry one. And I just really liked it. So here I am in nuclear.